Welcome to the Toronto Machine Learning Society's annual conference. My name is Aarti Malhotra, and I'm glad to be the moderator for today's session. I'm honored to introduce Dr. Ivey and Mr. Jonah today. Dr. Ivey has a Ph.D. from U of T. Her research work focused on understanding and modeling creativity and designer behavior in engineering design using cognitive psychology and natural language processing, and has published 20 AI conference and journal papers. Currently, she is the Applied AI R&D Lead in the Telus Data Strategy and Enablement team. She leads a diverse portfolio of internal and external data and AI R&D projects. Mr. Jonah is a mechanical engineer in the Mission Critical Environments team with expertise in energy efficiency, cooling system, and automation. He has a wide range of experience evaluating and implementing various new energy-efficient technologies in Telus facilities to reduce our carbon footprint related to power and cooling. May I now request Dr. Ivey and Mr. Jonah to enlighten us about how Telus applies model-based reinforcement learning to reduce energy consumption in data rooms. If anyone has any question, please feel free to post in the chat. We will have a Q&A session after the talk. Over to you, Dr. Ivey and Mr. Jonah.
Hi, thank you, Artie, for that great introduction. So today here, I am very pleased to present to you the Telus and Vector collaboration on being able to use model-based reinforcement learning to help reduce energy consumption in data rooms. So just first of all, going through some of the motivations and like giving you a preview of what we did. So first of all, we're motivated by being able to reduce costs and to reduce greenhouse gas emissions in the operation of data centers. So this includes heating, ventilation, and air conditioning costs. So what you would think of as HVAC. So just to give you an idea of, the energy required to operate data centers. So in 2014, it was estimated that data centers accounted for 1.8% of total power consumption in the US. And there are lots of challenges to optimizing the control of cooling and as well heating while considering other factors such as external weather. So these are things that so factors such as weather isn't something that you can necessarily control. However, what you can do is you can take a look at weather forecasts. And also what we're using here and what we're leveraging here, and we have plenty of in Canada, is that we're leveraging something called free cooling, which you could think of as being analogous to opening a window and letting in cold air. So based on this motivation and in our conversations with our collaborators at the Vector Institute, we recognize that there is an opportunity to apply model-based reinforcement learning, or MBRL, so the MBRL technique, to help reduce costs. So in our project, what we first did was we found that our simulation showed a potential energy savings of between 2.5% to 15%. And this is dependent on conditions, so various conditions such as the weather. And what we also did was, after we developed the simulation and the agent, we were actually able to pilot test this during hot summer months. And what we found was that this resulted in a 9% total building energy savings, which is fantastic. And in the course of developing the MBRL model, what our lead scientist also did was that they developed something that he termed hyperspace neighbor penetration, which is an algorithmic innovation to help deal with slowly moving variables such as temperature. So in the rest of this talk, what we'll do is we will discuss the journey to deliver this AI solution basically from concept. So from the idea that, we are motivated to reduce energy costs to actually an on-site pilot test. And then we'll also talk about some of the next steps that we envision for this project. So just quickly, first of all, a little bit about both Telus and Vector. So Telus is a dynamic world-leading communications and information technology company. And one of the things that we are committed to doing is to be able to use our technology to enable remarkable human outcomes. So I think a lot of you are probably familiar with Telus on the telecommunications side, but we span across 10 industry domains, including the telecommunications that you're probably familiar with, as well as other sectors such as health and agriculture. And one of the motivations for Telus to be undertaking this collaboration is that we have a goal to reduce our energy consumption by 50% by 2030 as compared to 2020 levels. So now a bit about the Vector Institute. So the Vector Institute, their mission is to drive excellence in leadership in Canada's knowledge creation and use of artificial intelligence to foster economic growth and to improve the lives of Canadians. And what you'll notice is that they have over 900 industry program participants, of which Telus is one of these participants in this specific project. So then we've talked about Telus, we've talked about Vector. How did we actually get together for this, Telus and Vector collaboration? So first of all, this falls under the general umbrella of AI for Good initiatives. And also, Telus is a founding sponsor of the Vector Institute. So when this project was proposed, we could see that there were very much in line with our mission, some of our sustainability goals, and that's where we started collaborating together. And on the right is just a screenshot of a success story that was published earlier this year, and the link is below if you want to read it, and we can certainly distribute this later. So now I'm going to pass this to Jonah so that he could talk about some of the roadmaps to carbon neutrality that we have as targets.
Yeah, thank you, Ivey. So yeah, Telus sustainability has been part of the culture for many years. Since about 2000, we've been publishing a sustainability report every year. And so where we stand now is we've just reached our first set of targets that came due in 2020, and we've basically reset for the next 5 and 10 years. So we consume quite a bit of energy across all our data centers and telecom facilities across the country. So it's about 1 million megawatt hours of energy per year, 80% of which is considered scope 2, so electricity consumption, and 20% is scope 1 type consumption, which is direct fuel consumption, whether that's diesel fuel for generators, our auto fleet, and or natural gas for heating. And so where we're headed for 2030 is that by 2030, we've now set a target to be 100% carbon neutral in our operations. In addition, by 2025, so 5 years earlier, 100% of our electricity will be procured by fully renewable or low carbon sources. And as Ivey mentioned, we'll reduce our energy intensity, so the megawatt hours per terabyte of data traffic processed on the network by 50% by 2030. A new one that's been recently added to the list is there's also going to be an absolute reduction, or we're aiming for an absolute reduction in our GHG emissions for both scope 1 and scope 2 consumption of 46% below 2019 levels, so between 2020 and 2030. So all that across energy and GHG, so greenhouse gas emissions, it's very important to Telus, and very much a part of what we're working to do over the next decade. Next slide, please, Ivey.
Yep.
And so in light of this collaboration that Ivey described, we basically got to brainstorming, and we're wondering, could model-based reinforcement learning, so this AI technique, be used to actually decrease our energy consumption related to HVAC, so cooling and heating of our telecom facilities and data centers. So for those who don't know, Telus, we have cell towers across the country, but in addition, we also have what are called central offices, so telecom facilities in each neighborhood and city where we provide home services, and home and business services to customers. So we're talking thousands of facilities with network equipment, so switches, routers, servers, which are powered 24/7 and need cooling 24/7. So about 30% of our electricity consumption actually goes toward cooling, meaning that if we're able to take any percentage saving on the cooling side, even if it's small percentage, at scale there could be quite a large impact, both for Telus toward achieving our targets, but also as a better, good impact for the environment. And so we basically came to the conclusion that applying some sort of AI-based control algorithm to our control systems or building management systems that are what control the cooling system in our central offices and data centers is where we could have a good opportunity to achieve this saving.
All right. So now I'm going to just move on and give like a very brief primer on reinforcement learning, and also talk about what this meant for us practically in trying to implement reinforcement learning. So reinforcement learning is a technique that seeks to maximize rewards for a set of actions that can be taken. And these rewards, or penalties, if you want to think of the inverse, depend on the desired value, which is defined in a policy, and the model of the system or the environment. And a lot of times the example given for reinforcement learning is that it's very similar to how people or animals will learn to interact with their environment. So what you'll see is that, when young children learn to walk or talk, they interact with the environment, and based on the feedback, they will adjust sort of, their behaviors so that at one point they'll learn to talk and they'll learn to walk. So reinforcement learning is considered one of the techniques that's the future machine learning. It is goal-oriented. It's considered innovative. It looks at being able to achieve long-term results, and it doesn't require a very large data set for training. So at the crux of this is that we have an environment and we have an agent that interacts with the environment. So what this means for us in terms of the project itself is, first of all, we built a virtual simulation environment, and this provided for a safe testing environment where we weren't at risk of basically frying any expensive and crucial IT equipment. And what this also allowed us to do was it allowed us to speed up the learning. So we were able to acquire hours and hours of real world experience in seconds. As we talked about before, things like temperatures and weather are very slow moving variables. So it could take a very long time to actually gather that data if we were waiting to see, what happens when we were to heat up this very large space, even by 1 or 2 degrees. And then we built an agent for the simulation using model-based reinforcement learning. And one of the algorithmic innovations that came out of this work was something that we term hyperspace neighbor penetration, which is used to deal with these very slowly moving variables. So then when we put this all together, what we thought of it was like, this is like a chess game. We were having our agent play a chess game with controlling the temperature and the energy in our data rooms. So we set a goal for it, which was to regulate the indoor temperature to be at or below a certain set point. And that is based on, the equipment sensitivities. And we also said we wanted to be able to minimize energy consumption. There are other requirements that we also had to satisfy, so such as allowing the compressor to rest enough between cycles, because you can't just turn the compressor on and off in an air conditioner repeatedly. So then what this came down to was that there were basically 3 options that had to be chosen on a minute-by-minute basis. So option 1 was to run the compressor. So this is air conditioning as you would normally think of it in your house or in your office. So as we all know, this is a very effective cooling, but it's also very expensive, or very expensive relatively speaking, because it requires a lot of electricity. There's option 2, which is to run free cooling, which is effectively, you could think of this as analogously as opening the window and letting in the cold air. So this is a much less expensive way of cooling, but it's also not as effective, and it's also subject to conditions. For example, if it's very hot outside during lunchtime, you cannot necessarily use free cooling. And then there's option 3, which is just to idle all the systems, which is basically let everything not run. And this minimizes the cost, but there is no cooling effect. So what we also look at here is that we are not necessarily trying to optimize for the next step, but we're trying to optimize for a longer time period, which is typically in over 12 to 24 hours. So like over the course of a day. So it is more long-term optimization. So then just to take you quickly over the simulation results. So when we started running the simulations, we observed that, you know, there were 4 strategies that the AI developed amongst a bunch of them. But the ones that we noticed that that were employed the most were, 1, don't overcool. So conventionally, you know, the air conditioner would run to a certain set point. But here, because there was the additional input of a forecast, the agent could look over a longer period of time and decide not to overcool. Also, the agent knew that it could sacrifice short-term gain for, or rather short-term, or it could endure short-term pain for long-term gain. So what it'll do is it'll look over a longer period of time rather than the immediate minutes or next steps. It was also more flexible with using the compressor, in that it wouldn't necessarily run the compressor till it reached a certain set point, but it would run the compressor till it was just cool enough. And then it was also more flexible with free cooling, in that it recognized that, oh, well, if I open the damper and let the cool air in, I can achieve the same effect because of that that goal of minimizing energy usage. So based on the simulations, we were able to estimate that there's between 2 to 15% annual savings that could be accrued from this. So now I'm gonna pass this over to Jonah to talk about the continuous testing results.
Yeah, thank you, Ivey. So once we had those simulation results in hand, we essentially went forward and deployed this AI algorithm in a pilot site, basically a small 10 by 10 shelter with some network equipment in it in Southern Ontario, and followed the results. So after several months of collecting data between June and August of this year, we basically took the data, ran a weather-corrected regression analysis on the data to ensure that you know, different hot or cold conditions, you know, that were different from the baseline were accounted for. And what was you know, very pleasantly surprising is that we actually exceeded that 50% saving that Ivey mentioned that the simulation predicted, and we achieved in that time period 18.6, so almost 19% energy savings just on the HVAC unit alone. And keep in mind that was in the summer months. So throughout a whole year, we'll be able to tell what the savings will be. But it was quite promising at that point that the savings were that good in hot weather.
All right. Next slide.
Next slide, please. Yeah. And so basically, overall, to kind of summarize our experience from start to finish, deploying this in the real world. You know, there are definitely some challenges that we had and that we had to overcome to start from idea to actual implementation. And you know, that's no surprise because only 15% of large organizations have actually successfully deployed AI. So it's quite new, but as long as you take things slow, step by step, you know, it is doable. And we did see that here by starting small with a pilot project and taking it from there. You know, everything from having the simulation in this case, which allowed us to present to and explain to, I mean, ourselves and also the network and building operations teams how the HVAC unit was actually going to be controlled once the AI system was in control, was very much a big help to understand what the real world impact would be. And besides that, you know, actual integration between the two systems was sometimes a challenge if well, we encountered certain bugs on the HVAC controller's software and firmware that we worked with the vendor to fix to be able to work properly with our AI control system. But that being said, you know, we were very pleased that it was a successful pilot deployment. We even added on heating control to the AI after cooling was successfully demonstrated, and this pilot site continues to run today. So from there. Basically, we were looking to what we could do in the future with this AI control system. So we have, as I mentioned, thousands of buildings across the country with different manufacturers of HVAC units and control systems, so the BMS systems. So we would definitely like to scale, but how exactly to do that in the best way is something that we're thinking about and working through. Another thing that's being considered is how to apply this control system to other business units. So we have our core telecom business, but Telus also has an agriculture arm, home solutions, maybe even health. So the AI could definitely be applied elsewhere. So that's something to be considered for sure. But because this AI was developed as part of an AI for Good initiative, the code that was developed is in the process of actually being open sourced to be able to be deployed, in the wider community and increase the benefit of it. So I'll pass it back to Ivey if you have any closing words for us here.
All right, thank you, Jonah. So just to close off, I think this is just this project is just one of the many examples how Telus and how we are using our technology to help make the future friendly. So having closed with that, we'll move to questions, and we're happy to discuss all the journey that we just presented. Thank you.
Thank you, Dr. Ivey and Mr. Jonah. It was a great talk. We'll go to the questions. Sankalp has a question. Dynamical systems such as the data centers are quite complex to model. How did you build the virtual simulation or the digital twin of the data center for training your agent?
Yeah, so I'll take this. So one of the challenges that we had with this project was actually sourcing a data room, not even data center to start with, but a data room that met the requirements of actually having enough historic data that we can use that to first build a simulation and then train the agent. So we actually had to go through a whole list of rooms and kind of like probe it to see, first of all, does it have all the data that we need? Is it connected? Because not only does that help with us to obtain the data, the historic data, but what you probably can see from here is that we need to actually remotely access the room so that we can issue these commands. So those were some of the challenges that we definitely faced, is to find a room that met all the criteria for us to even start working with it. So yeah, that's how we went about being able to build the simulation environment.
Okay, that's great. Next question from Said. Did you also have any consideration of the data center topology and circulation design in the model?
Jonah, would you be able to answer that one?
So in terms of the topology, would you be able to clarify?
Data center topology and circulation design in the model. I think the layout of the data center.
The layout, yeah. Right. So I mean, in this case, we started with a small shelter, 10 by 10. So there's really one heat source. There's basically one line of network equipment. So it was not a very complex environment with multiple HVAC units with airflow going in various directions, turbulence, etc. So I don't think there was, I mean, Ivey, from the model perspective, I don't think there was anything done as far as fluid dynamic simulation or anything.
Yeah.
But really more utilizing that historical data and how let's say weather impacted the temperature inside the space. I think that was more how it was done.
Yeah, that's correct, Jonah. I think that's partially why when we first looked at what we call like the medium to large rooms, and with multiple HVAC units and also like the non-homogeneous equipment inside, we realized that the thermal dynamics of that also has an impact. And at that point we said let's find something that is more manageable, right? So because we definitely had the goal of being able to show that this works like in a pilot site.
Okay, thank you. Next question from Lau. Are you using the same algorithms as that which were used by Google with respect to what they did with their data centers to reduce costs?
Yeah, that's a very good question, and that's actually something we're trying to find out. So Telus actually entered into a 10-year strategic alliance with Google, and as part of that, we are their telecom partner for the next 10 years to develop a lot of like the Google Telecom specific sort of features and functionalities of the Google Cloud. So one of the advantages for us definitely is that we get access to all the Google Smarts and the Google folks who've worked on things. So that is actually one of the questions that we're pursuing with the Google team to understand, is this reinforcement learning the same one that they used, that they published in their 2016 paper? And if so, is this can we just like do some work together, enable free cooling, and there we go. We have a cooling product that we could put into all of our large data centers and data rooms.
Okay, great. Next question is from Levi. How long did it take from initiation to production for your first live? How big is the team of developers?
All right. So this is a good question too. So from the time we started working on it, I think we first did the kickoff in March or April of 2019, and we were able to do our first like site testing, like not even testing the algorithm, but just understanding how the HVAC equipment worked on site. That was about this time last year. So that was it went from March 2019 to November of 2020 to just be able to get to the site, understand the site equipment, and then we finished the first like continuous pilot test in the summer of 2021. So that's sort of the timeline. And then in terms of the developers, we had one lead developer. So it was Vincent, and I indicated that on the title slide. We had a few others who helped him along the way, but he was the main developer. What one of the takeaways that we took from this, it's we need a lot of support in terms of the integration piece. So basically the communication APIs, the building management systems, and then the integration between like all the pieces together was the part where we needed a lot of support from a lot of sort of different teams. So definitely one of the recommendations that we've put through for this going forward is that we have a dedicated cross-functional team to look at this. So yeah, I think the lesson here is this is why only 15% of organizations have successfully implemented AI, because of these challenges.
Yeah. Thank you. Next question from Jennifer. With net zero mission from the globe, what do you envision of future of data centers? That is, more green energy to take place, etc.?
Yeah, absolutely. So, data centers are growing and growing in size. If you look in Canada alone, Amazon just announced, for example, they're deploying in Calgary in an AWS instance. Google has in Montreal, Toronto. We at Telus have various data centers across the country. And the quantity of data stored and processing data centers is constantly increasing. So definitely having data centers located strategically in places where the source is actually clean. So whether it's on hydropower or it has a solar offset component, I think that's going to be very important to help offset the emissions that are generated from the large data consumption. What's interesting, Google specifically, they announced that they're working towards a future, I believe, where because they have data centers across the world, so at 12 noon in Europe, they could be generating clean energy with solar power, and then so you could run your application on solar power in a different instance in, let's say, in Europe, and then transition over to North America when now solar energy would be higher here. So that's something that Google announced that they're working on, which is just one of the ways where, being creative and strategic with data center location utilization will help toward offsetting, large consumption, I'd say.
Thank you. I think we can take one last question. Kay has a question. In terms of scaling as deploying to more data centers or rooms, would it be independent RL agents for each center or each region? How do you plan on balancing learning common attributes of various data centers versus learning uniqueness of each region and center?
Yeah, I'll start with this one. So we anticipate that, for sure there would be training and sort of tuning of each agent in each data center, which is why one of the next steps that we are looking at is we're not necessarily looking at these small data rooms. So across a wireline, so mobility and wireline and wireless network. So wireless is the mobility side. There would be hundreds, if not thousands, of these rooms. So one of the ways that we think we would actually be able to make an impact, both from the greenhouse gas emission side of things, and also like on the the electricity bill that comes in monthly, is that we would put this into the large data centers. And fortunately, we don't have that many of those. So we definitely need to see how we would run it. And also one of the things that we sort of envision happening is that we would see how we could run this in GCP, so it's more centralized as well. So whether it's like different GCP instances, or like one GCP instance for like a whole region, we've yet to see that because we haven't done that work yet. But definitely, like we recognize that there would be, retraining and tuning for each deployment because of the differences, even in something like temperatures and precipitation, which will affect, the conditions that occur inside the room.
Okay, thank you. I think we're running out of time here. But on behalf of the MLS team and everyone here, I would like to thank you, Dr. Ivey and Mr. Jonah, once again. And I encourage attendees to attend our partner booths for exciting giveaways.
Yep.
Thank you so much.